This is the second part of Chapter 4 narrated slides for Chem 200. This would fall under week 4 of our class, but I opened up weeks 3 and 4 at the same time just because it's all Chapter 4. So make sure you've watched part 1 first, as you would have missed some important material if you started with this set. So last week we talked about precipitation reactions. This week we're going to deal with acid and base, gas-forming reactions, and oxidation and reduction reactions. This is also called redox reactions. You may have heard of it. Our text doesn't go into a whole bunch of detail with gas-forming reactions, so we're going to kind of supplement with our own kind of information regarding that. So before we get into some new types of reactions, this is kind of a follow-up to last week's lecture slides. This is a problem I encourage you to try on your own. I have posted a video of me going through how to solve this problem. This video is a required video for you to watch. It is the Lecture 3 video. Because of the holiday, it's not a part of our synchronous class because technically Monday is a holiday. So you have until September 10th at 8 a.m. to watch it. If you do not watch it, you will not get the points for the video. And just to make everyone aware, you do need to actually watch the whole video to get the points. I have noticed a lot of students have started to just kind of go to the page, start it, and then forward through till the end. Excuse me. I can see that. So you do need to watch the whole video to get the credit. Okay. So moving on to a new type of chemical reaction. We're going to start talking about acid-base reactions. We'll deal with acids and bases much more later on in the semester. So right now we're kind of looking at them in terms of just being a general reaction. So first we need to understand what is an acid, what is a base. There'll be two definitions that we go with. We have the Arrhenius definition and the Bronsted-Lowry definition. Your text goes into a lot more detail with this. I strongly encourage you to read it and ask me if you have any questions. We will predominantly be focusing on the Bronsted-Lowry definitions of acids and bases. However, you should be able to differentiate between them and identify acids or bases based off of those definitions. So if you do have questions from the reading, I do encourage you to ask questions so that we can make sure everyone is up to speed. So typically when we are dealing with the Bronsted-Lowry definition of an acid, we're calling something a proton donor. And when we're dealing with the Bronsted-Lowry definition of a base, we're dealing with a proton acceptor. So we're going to see examples of this in the next few slides. So acid-base reactions, as we said, acid would be a proton donor, base would be a proton acceptor. So it's kind of a give and take, just like we've seen with our cations and anions, maybe with electrons, something you're familiar with already. So we're going to kind of manipulate that now that we're using a proton instead of an electron, but the same kind of give and take reaction is occurring. Acid-base reactions are also often called neutralization reactions. If the acid is neutralized when enough base is added to react with the acid in solution. Again, technically you could say the same thing about base and adding acid. Just by convention, we talk about the acid being neutralized by a base. Hydroxide, which is also one of our polyatomic ions, is a very strong base. For the purposes of stoichiometry and calculations, it can be assumed that it reacts completely with any weak acid. So again, 100% reaction. We talked about last week the concept of complete dissociation, all that kind of good stuff. So, strong acids and bases will completely ionize in water. They are strong electrolytes. So, just like we talked about last week, that idea of dissociation, right? And that strong electrolytes dissociate 100% in water. Strong acids and strong bases dissociate 100%. I'll say that again. Strong acids and strong bases dissociate 100%. If I'm saying something multiple times, this should be something you're writing in your notes. Something like HCl, which is strong acid, fully dissociates in water. So if we see HCl-AQ, we know that really means that's that secret language of H plus and Cl minus. That's how it really exists in solution, right? HCl is a strong acid, therefore is a strong electrolyte. Strong bases also dissociate 100%. Weak acids and weak bases do not dissociate or ionize completely in water. So we get partial dissociation. So here's acetic acid. This is basically vinegar. And what we get is some dissociation. This should actually have an arrow going back the other way as well. But that most of it will exist in this form, but some of it will exist in this form. So this would make a weak acid and a weak base weak electrolytes. Strong acid, strong base, dissociate 100%, strong electrolytes. Weak acids, weak bases, partially dissociate, weak electrolytes. You should know these. If you need to write them down, you should. Again, moving on into your 201 days, you will need to know these strong acids and these strong bases. So let's look at some examples of this. Ammonia is a strong base. It's usually found as a gas. When it's dissolved in water, it undergoes a weak base reaction with water. Ammonia is our weak base. Sulfuric acid is our strong acid. So here's NH3 in aqueous, because we know it's usually a gas, but once it's dissolved in water, AQ, right? We're going to have NH3AQ. It's a weak base, which means we're only going to get partial dissociation. So here's our water. And in this case, the water is acting like the acid because it is going to donate a proton. And the NH3 is acting like the base and is going to accept the proton. Sulfuric acid, on the other hand, is a strong acid because the first hydrogen in this will dissociate 100%. However, the second hydrogen does not. So we have a strong and a weak acid in this. This is called a polyprotic acid because there are multiple hydrogens here. So the first time when we see H2SO4, we know that this will dissociate 100% into H pluses and SO4 minus. HSO4 minus. What we do know is that this could dissociate again. The HSO4 minus, there should be an arrow here, will dissociate again occasionally and become H plus and SO4 2 minus. This does not always happen, not 100% like the first one does. So when neutralizations occur, when acids and bases react producing water and salt. So here is the general equation of neutralization. Some acid plus some base yields water and salt. And I'm purposely color coding so that we can see where everything's coming from. The salt, right, the ionic compound, the anion will come from the acid typically, and the cation will come from the base. So here we have an example. 2HCl aqueous plus MgOH2 solid yields 2 waters and magnesium chloride. This would be the molecular equation, right? We could go through, do our complete ionic, our net ionic equation. We know that 2 of the H pluses from the HCl plus the magnesium hydroxide, we have to write the whole thing out because it's a solid. The only time we can get rid of spectator ions are if they're actually ions. This is a solid. It's not an ion, so the whole thing has to go in there. Yields 2 H2Os and magnesium cation. So, again, that would be a strong, the previous example was a strong acid, strong base. Let's see what happens with a weak acid and a strong base. So HF is a weak acid. It does not dissociate 100% in water, but NaOH is a strong base. It does dissociate 100% in water. So molecularly, this would be the equation. Yields water and a salt, just like we talked about. And again, we have our weak acid, so we have to keep the whole thing together in our net ionic equation, plus just the portion of the hydroxide that is the ion, yields water, and F minus. Remember, WA and WB stand for weak acid and weak base. They're not ionized very much, so we don't write them as ions in the equation, right? That's why this HF stays as HF. So, how can we kind of set some guidelines for ourselves so we know kind of how to go through this? First, when we're doing these acid-base neutralizations, we should always list all the species present in the combined solutions before any reaction occurs, right? We want to decide what reaction is going to occur. And then, as always, make sure it's balanced. We can't really move forward with anything until things are balanced. And then we can write our net reaction, or our net ionic equation from this, right? This would be breaking up everybody into their ions, that secret language that I know that you know, that when we see aqueous, it really means that we have the cation or the anion present. Only for strong acids and strong bases. The weak acids and weak bases we keep the same. We would have to determine a limiting reactant if we needed to go that route. And we calculate the moles of the required reactant, or the product, if that's what's being asked, and convert to grams, or volume of the solution. So here we're going to go through an example of putting all of those steps together. In a certain experiment, 28.0 milliliters of a 0.250 molar HNO3 solution is mixed, right, with 53.0 milliliters of a 0.320 molar KOH solution. What is the concentration of the H plus or the OH minus ions that are in excess after the reaction goes to completion? Well, before we can answer the question that's being asked, we're going to have to turn these words into an actual chemical equation. So that's what we're doing here. I've gone ahead and we're going to color code some things so that you can kind of keep track of who's going where. You'll notice that I have rewritten water, H2O, a little differently. This is to kind of help guide you in seeing where the H and the OH that make up the H2O, where they come from. It's still water and a salt. All that's the same. I just wrote it a little different so that we can kind of use it as a guide. So, like anytime we have a chemical equation, the first thing we always should check is if it's balanced. Because if it's not balanced, we can't move on to step 2. So I would encourage you to take a moment, pause the video, balance the equation. And then we can move on. Then we can move on from there. So use the given amounts to determine the moles of each reactant. Think molarity, right? So we were given the molarity of each of these. We were given the volume of each of these. If I have molarity and a volume, I can figure out number of moles. So I can determine the moles of each of these guys. So that's what we're going to do. We know that molarity is moles of solute over liters of solution. In this case, liters of solution would be the total solution. So in both cases, you're going to have to look at what you have. So we have a starting materials, and then on the reactant side, the total solution will be the total volume of both of these together. So for our starting materials, we have our 0.0280 liters of our HNO3 times our 0.250 molar, there should be a 0 there, sorry, 0.5 molar solution. 3 sig figs in both cases, sorry, again, there should be a 0 there, so 3 sig figs. We're going to hold out that 0 there just to highlight it. Same for the KOH. So now we have an amount in moles of 2 different starting materials. So that should be your hint. Whenever I have given amounts of 2 different starting materials, I'm going to have to do limiting reactant. That's where my brain should be going. So we know that if I have the moles, I can figure out how much of this and how much of this will neutralize, right? We know that the H is coming from the acid, the OH is coming from the base, and that when we make water, that's neutralizing it. So do we have any excess, right? We were told we're trying to figure out the excess. Do we have any excess of the H plus? Or do we have excess of the OH minus? So that's what we're going to use our molar ratios to help us determine. So when we looked at our balanced chemical equation, right, we can see that it's a 1-to-1 ratio of our acid to our base, which means we can go through and say that the given moles of the KOH that we had minus the given moles of the HNO3, we have more KOH than HNO3, so we're going to have an excess of KOH, which means we're going to have an excess of the OH ion. The example in the book uses the products method for finding the limiting reactant in this step. You'll get the same answer, but the sig figs will be slightly different. So I'm trying to show you a different route. Both are totally fine, acceptable, correct ways to do it. It's just a different method of solving. So if you haven't realized, this is a direct question right out of your textbook that we're going through in detail. So next, now that we know the moles in excess, we can calculate the molarity of the OH ion after the reaction is complete. So if I know I have this many moles of KOH, and it's after the reaction is complete, so we've combined our two volumes. So our new molarity, that total volumes, right, liters of solution, has to be the 28 milliliters plus the 53 to get this. So we end up with a molarity of our OH minus concentration. Now, we're going to take a look at what would happen if you wanted to know, based off of this reaction, if there was an H plus concentration. You may be saying, well, how could there be an H plus concentration? We used it all up. This reaction goes back and forth, right? That double arrow, that two-way street. So a little bit of it will still be formed. Not very much, though. So what we can do is use this kind of flow chart right here. Again, we will be talking about this in much greater detail later in the semester. I just like to introduce it now as a way to show students where we're going with things. But basically, it allows you to go from pH to the H plus concentration. When we see these brackets around things, that means concentration. Okay, so the molarity. So we can go from pH to the molarity of the H plus ion. From the molarity of the H plus ion, we can go to the molarity of the OH minus ion to the POH. So it's kind of like a little, and then POH to H, little trend. And you can follow the arrows, are all color-coded to kind of help you guide along. But what's important here is when you do calculate it out, we see that the H plus concentration is impossibly tiny. Very, 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 very tiny. That's because, if we went back to our previous slide, we know that we had OH left over, KOH left over. So just that 10 to the negative 14 is just this tiny little bit that's going back in this direction. So not a significant amount. So that's the introduction to our acid and base neutralizations. We're also going to see gas formation reactions. Like I said, your text doesn't go into a lot of detail with this. We have a really good lab where we deal with this when we get to the antacids lab later in the semester. But basically, when you think of gas formations, think of like Tums, or not Tums, what is it, Alka-Seltzer and that kind of stuff, right? Things that form bubbles. So there are many bases out there besides things that contain OH. A lot of these form molecular compounds such as CO2 or H2S, which is very, very stinky, smells like rotten eggs. So salts containing a carbonate or a bicarbonate ion react with acids to form bubbles, right, in the form of CO2 gas. So here's an example of that. Here's a carbonate plus a strong acid. And what we will get out is a salt and this carbonate, which will further break down into water, CO2 gas, and a salt. So when we have this kind of reaction, the products we will get will be water, gas, and salt. Just like when we had acid-base neutralization, we said that the products were water and salt. Now we have gas as well. And basically that is because this compound right here is not stable. It can exist momentarily, but it automatically will break down into water and gas. So when we write the net ionic equation for this, we'll have H plus the HCO3 minus yielding H2O and CO2. This is an example that's also in your text, but I'm going to encourage you to try this one on your own and then see how you did. The other type of gas that we often form is H2S. These are with sulfides. You know you're dealing with a sulfide when you have a very stinky reaction. It often smells like rotten eggs or like a fart. So here we have sodium sulfide and a strong acid. Again, we're going to get the H2S gas and our salt out of it. There are other gas-forming reactions beyond this. These are just the two most common ones that we're going to interact with, especially when it comes to lab, will be the carbonates and the sulfides. So these are the ones that I'm asking you to know. The last type of chemical reaction that we're going to talk about in this chapter are oxidation-reduction reactions, also called redox reactions. I'm going to go through these in the slides here. I have also posted a more in-depth lecture slide to kind of help guide you through if you're really struggling with redox, as well as some really good resources posted in the videos. So I encourage you to go check those out as well as read your text. So oxidation reduction reactions, or these redox reactions as I'm going to call them, are common in a lot of different types of reactions. We see it in some precipitation reactions. We see it in some single displacement reactions. Different kinds of reactions. So something could be a precipitation reaction and also be a redox reaction. That's not mutually exclusive. For atoms and covalent bonds, the oxidation state refers to kind of an imaginary number the atom would have. So it's this idea that we're going to pretend if a covalent compound were to behave like an ionic compound, and kind of, you know, if we broke up that covalent compound, who would own the electrons? That's kind of what we're looking at here. There are some rules that we're going to go through with this, so that will hopefully help clarify things for you. In ionic compounds, it's very, very easy. The oxidation state is equal to the charge of the ion. So those ones are easy for people. Electronically neutral compounds, the sum of the oxidation states must be 0. So if I have a compound that does not have a charge on it, all the oxidation states need to sum up to 0. Some oxidation states will be negative, some will be positive. Overall, they all have to add up to be 0. A time when you would have a not electronically neutral compound would be something like a polyatomic ion, in which case the charge on the polyatomic ion has to equal the sum of the oxidation states. And then we will write them as plus the number or minus the number. So let's look at some examples. Here we have some rules. Again, these rules are something you should be comfortable with, and I would strongly encourage you to memorize these. If you don't, you're going to have to write them down. Remember, you will not have access to your textbook or any of the printed resources online when it comes to your assessments. So if you do not feel comfortable being able to memorize these rules, that's something you're going to have to do. But again, when you get to 201, you will be expected to know these rules. So the first rule is an atom in its elemental form is always going to have an oxidation state of 0. So what do we mean by that? An elemental form of something. We know that most of our metals exist as solids. So if you see sodium solid, hydrogen gas, oxygen gas, now remember, those would have to be diatomic. That would mean that all the oxygens, both these oxygens, or if we have ozone, all three of these oxygens all have an oxidation state of 0. Mercury exists as a liquid. All of those would have a 0 oxidation state. If we have a monoatomic ion, right? So something like a sodium cation or a chloride anion, the charge associated with that ion is equal to the oxidation state number, plus or minus. For the purposes of our class, a fluorine, when it's in a compound, will always be a -1. So whether it's HF, PF3, whatever, that will always be a -1. Oxygen, 95% of the time will be a -2, except for when we're dealing with peroxides. So in the case of water or CO2, the oxidation state on the oxygens here would be -2. And again, for the purposes of our class, hydrogen will always be a +1. And then anything else, you will have to kind of base it off of these rules that we see to determine what the other oxidation numbers would be. So carbon can change. Carbon could be a 0, a 1, a 2, a 3, a 4, or 6. Depends on what the compound is. So let's look at assigning some oxidation states to all the atoms in the following compounds. We have CO2 and NO3-. So in CO2, we look at it and we say, okay, so this is electronically neutral. There's no additional charge on this, so we know that all the oxidation states have to sum up to 0. And we know that our rule for oxygen is each of these oxygens is a -2, right? Just like we see here. So -2 and -2 would be an overall -4, which means this carbon must be a +4. And NO3-, we have an overall negative charge, so we need to keep that in the back of our heads. Each of these oxygens is a -2, so that's an overall -6, which means if this were a neutral compound, the nitrogen would be a +6. However, we have a negative charge here, so the nitrogen is a -5. It's important to remember, you cannot say the O's, or the O. Each oxygen is a -2. A lot of students kind of forget that portion of it when they're talking about it. So these oxidation reduction reactions, the reason we call them redox reactions is if you have oxidation occur somewhere, you have to have reduction also occurring somewhere else. So it's a yin and yang kind of thing. If someone is increasing in their oxidation state, they are losing electrons, right? Which means they are being oxidized, and that means something else is gaining the electrons, right? The electron doesn't fly off into space and never to be seen again. In a reaction, someone is giving it up and someone is taking it. We also have the concept of an oxidizing agent and a reducing agent. This is sometimes tricky for students, and I have a lot of really good resources for you. I also encourage you to read the text on this. But mainly what it comes down to is the oxidizing agent is the thing that causes oxidation to happen. So the compound or the element or the atom that is oxidized can never be the oxidizing agent. Something else is. Something else caused that element, atom, whatever, molecule to be oxidized. Same thing happens with the reducing agent. It's the thing that causes reduction. So we're going to go through and look at some examples of this. These are some good examples where we'll see some oxidation reduction occur. And we'll go through the process. So we start out with this top reaction right here. And what we're going to do is we're going to go through and call out the oxidation number of each atom in each compound. And then we can see how they change. So in the first step, we go through and we see that our lead, because it's lead 2, would be a +2. And the sulfur would be a -2. Each of our oxygens, they're 0 because oxygen is in its elemental state. Then on the product side, we have the lead still is a +2, the oxygen as a -2, the sulfur, and each of the oxygens here as a -2. So when we look from one side to the other, The oxidation state of the sulfur atom went from being a -2 to a +4. So the sulfur was oxidized because it lost electrons, right? It became more positive. We know that electrons are negatively charged, so it was oxidized. So we're saying the sulfur was oxidized, and the oxygen went from 0 to, on this side, in both cases, -2. So the oxygen was reduced. In the last step, again, as we go through it, we see that the lead started as a 2, oxygen as a 2, the carbon as a 2, the oxygen as a -2. This time, lead solid. Solid lead. That's going to be elementally pure. That's going to be a 0. And then we have carbon at a +4 and oxygen at a -2. So the lead, the lead is reduced. Its oxidation state went from +2 to 0. And the carbon went from +2 to +4. This is oxidized, right? Oxidation state increased. We went up. The numbers went up. So it is going to be oxidized. These numbers went down, so they are reduced. That is the end of chapter 4. I strongly encourage you, if you are struggling with the redox reactions, to go look at the supplemental materials as well as the worksheets that are at the end of chapter 4. They're really, really handy. They all have keys associated with them. I strongly encourage you to try to solve the problems before looking at the key. One of the big downfalls I want to talk about is please do not wait till the last minute to work on all of this. There's 2 weeks worth of work here. So please don't think, oh, weeks 3 and 4, I'll start this on Thursday of week 4. You need to start early. Complete reading of chapter 4. This material covered 4.6 through 4.9. We won't be dealing with 4.10. You'll start working on that when you get to Chem 201. You have to complete homework set 5, which is on chapter 4 in the the week 3 module. You won't find a link to it in the week 4 module. It's in the week 3 module. Make sure you watch our lecture video. You have until September 10th to make it happen. There's no discussion board this week. However, everyone is welcome to post in the peer-to-peer, ask some questions, share some ideas. That will all be very, very helpful for you moving forward. And then there's no synchronous quiz because of the holiday, so enjoy that. If you have any questions, please let me know.